My name is OOI WEI FENG. Today, I am going to talk about vectors in navigation. So, what is vector? Vectors are defined as a quantity that has both size and direction. It can be represented as arrows indicating direction and length. The picture beside is a vector. Vectors can be applied in many fields, such as physics, medical, engineering, navigation, and aviation. First of all, I will explain about the application of vector in navigation. Vectors are used to determine position, direction, and movement in navigation. It helps adjust for external forces like wind, ocean, currents, and terrain obstacles. Besides that, vectors enable accurate road planning and travel efficiency. Lastly, vector addition is used to calculate the resultant velocity and adjust movement accordingly. Now, I will explain about the importance of vector in navigation. The first important is determining direction and magnitude. Vectors help in defining the exact direction and speed of a moving object. In navigation, knowing both the speed and direction is crucial for reaching a destination efficiently. Imagine a ship traveling at 80 km per hour northward. This movement can be represented as a vector where the magnitude is 80 km per hour and the direction is north. Without vectors, would not have a clear way to represent or calculate such movement. The second importance is course correction and pathfinding. Vectors help pilots and sailors adjust their routes based on wind or ocean currents. For, a- for example, if an airplane is flying east at 500 km per hour but encounters a crosswind blowing south at 100 km per hour, the pilot must adjust the plan's heading. By using vector addition, they can determine the new direction to compensate for the wind. The third importance of vector in navigation is relative motion and velocity calculation. When multiple moving objects are involved, vectors help in calculating their relative motion to avoid collision and ensure safe travel. For example, air traffic controllers use vectors to track the speed and direction of airplanes. If two planes are on a collision course, vector calculations help determine how to adjust their speeds or directions to avoid an accident. The last importance of vector in navigation is emergency maneuvers. In rescue operations, vectors help in determining the quickest and safest ways to reach a distressed vehicle or person. For example, if a rescue boat needs to reach a ship in distress while strong ocean currents are pushing westward, the rescuers use vectors to navigate efficiently. They calculate the necessary direction to counteract the current and reach the target as quickly as possible. The first example is airplane navigation. Airplanes are constantly affected by external force, particularly wind. If a pilot only considers the plane's intended direction and speed without accounting for wind resistance, they may end up off course. To avoid this, Pilots use vector addition by adding the airplane's velocity vector and the wind's velocity vector. They can determine the actual velocity of the plane relative to the ground. This helps pilots adjust the plane's headings accordingly, ensure that it stays on its intended flight path, and reach its destination safely. The second example is maritime navigation. Just like airplanes, ships are also influenced by external force such as ocean currents, tides, and wind. Even though the ship's engine provides thrust in a certain direction, this external force can push the ship off course. Navigators use vector analysis to calculate the ship's resultant velocity and make the necessary course corrections. This ensures that the ship remains on track and reaches its destination in the most efficient way possible. The last example is GPS and land navigation. Modern navigation systems such as GPS rely heavily on vectors. Satellites can track the position and movement of vehicles using vector components. GPS systems calculate an object's speed, direction, and location to provide real-time navigation assistance. This can help drivers find the most efficient routes while considering obstacles, traffic, and road conditions. Thanks to vectors, GPS technology allows us to travel with greater accuracy and convenience. I will give a calculation of vectors in navigation. The question is, two airplanes, plane A and plane B, are flying in different directions while experiencing a crosswind blowing west at 50 meters per second. Plane A is flying north at 250 meters per second, while plane B is flying east at 200 meters per second. Besides, there is a picture showing all the information from the question. Question A. Determine the resultant velocity of each airplane considering the wind. So we need to find the resultant velocity for plane A first. The resultant velocity for plane A is, we just need to add up the original velocity and the wind velocity. The original velocity is 0I plus 250J, while the wind velocity is negative 50I plus 0J. And at last, we will get the resultant velocity of plane A is negative 50I plus 250J. So, if we want to find the resultant velocity for plane B, we need to add up the original velocity of plane B and the wind velocity. After we adding up two of them, the resultant velocity of plane B is 150I plus 0J. Question B. Calculate the actual speed of each airplane relative to the ground. The actual speed is the magnitude of the resultant velocity. The speed of plane A, we can find it using Pythagoras theorem method, which is square root negative 50 square plus 250 square. negative 50 square is equal to 2,500 and 250 square is equal to 62,500. So after we adding up two of them, we will get 65,000. And we need to square root 65,000 and we get the actual speed of plane A is 254.95 meter per second. After we finding the actual speed of airplane A, we need to find the actual speed for plane B. Same as finding plane A, we need to use the Pythagoras theorem, which is square root 150 square plus 0 square. 150 square is equal to 22,500. So if we square root 22,500, we will get the actual speed of plane B is 150 meter per second. Question C. Determine the displacement of each airplane after 2 minutes. So we know that the formula of displacement is equal to velocity times time. It's given that time is 2 minutes, which is equal to 120 seconds. And the resultant velocity of plane A is equal to negative 50I plus 250J. And the resultant velocity of plane B is equal to 150I plus 0J. For the displacement of plane A, we need to find the displacement in the x direction first, which is west direction. So we just need to use negative 50 times 120, which is equal to negative 6,000 meter. And we divided by 1,000 to change it to kilometer, which is 6 kilometer to the west. For the displacement in the y direction, north, we need to use 250 times 120 and we will get 30,000 meter, which is 30 kilometer to the north. After we found the x direction and y direction displacement, we can find the total displacement of plane A by using the Pythagoras theorem, which is square root negative 6,000 square plus 30,000 square, which is equal to square root 36 million plus 900 million, and which is equal to 930 million square root of 930 million, and we will get the final answer is 30.6 kilometer. After we found the displacement of plane A, we need to find the direction in angle. So the right direction is we need to use the tangent formula, which tangent theta is equal to 6,000 over 30,000, which is equal to tangent inverse 0.2. So that the theta is equal to 11.3 degree west of north. So if we want to find the displacement of plane B, we need to find the displacement in x direction first. The displacement in x direction is 150 times 120, which is equal to 18,000 meter and is equal to 18 kilometer to the east. So for the displacement in the y direction, north, It is zero because there are no movement to the north. So we can find the total displacement of plane B by using Pythagoras theorem method. The total displacement of plane B is equal to square root 18,000 square plus 0 square, which is equal to 18,000 meter, and it is 18 kilometer. So for directions, since there are no northward movement, the displacement is directly east. In conclusion, vectors are essential in navigation, providing a mathematical framework for accurately determining direction, speed, and position, whether in aviation, maritime travel, or GPS-based land navigation. Vectors help account for external forces such as wind and ocean currents, ensuring precise route planning and cost adjustments. By using vector addition and analysis, pilots, sailors, and drivers can make necessary corrections to reach their destinations efficiently and safely. Overall, the application of vectors in navigation enhance accuracy, efficiency, and reliability, making them a fundamental tool in modern transportation and travel. This is the reference that I use in my continuous assessment. That's all from me. Thank you.